So this lesson's on orthogonal vectors. So what does that word mean? What is orthogonal? Well, we tend to use the word orthogonal when we talk about vectors that are perpendicular. So just keep that in mind, that orthogonal equals perpendicular. And reflecting on what we learned back in algebra, if I have a line like this, y equals 2/3 x plus 5, we know that the slope here is 2/3. And we also know that slope is change in y over change in x, right? y2 minus y1 over x2 minus x1. So in terms of the direction vector, what would that be? What's the direction vector of this line? Well, we know vectors are of the form change in x comma change in y. So the direction vector of this line would be 3 comma 2. Let's call that direction vector u. Again, change in y is 2, change in x is 3, slope is 2/3. And if I want to get a line that's perpendicular to that, I need opposite reciprocal slope. So I've got to flip the 2/3 to 3/2, and I have to change the sign. It's positive here, make it negative here, and then the y-intercept is essentially irrelevant. So the slope again here is going to be -3/2. Slope is change in y over change in x. So the direction vector here is what? The direction vector here is change in x comma change in y again. And let's call the direction vector here v. So the change in x is 2, and the change in y is -3. So again, we're just trying to connect this notion of orthogonality to perpendicularity that we learned back in algebra. But now let's look at these two direction vectors. I have direction u and I have direction v. Do we see anything interesting about those? What do we see with direction vector u and direction vector v? What would their dot product be? Can we think about the dot product? Well, let's look at it. What is u dot v? How do we do the dot product? Multiply the change in x's, 3 times 2, plus multiply the change in y's, 2 times -3. And I get 6 plus -6, which is 0. So I started with two lines. I constructed their two direction vectors, and I discovered that the dot product of the two direction vectors is 0. So does that indicate what a relationship might be for these concepts? And how can we relate them to what we learned previously? So again, in this case, the two direction vectors have a dot product of 0. And I want to reflect on that together with what we learned previously about the dot product and the angle between two vectors. So let's remind ourselves of that concept. If I have two vectors, if I have vector v, and I have vector u, and remember this vector on this side would have been u minus v, but our main concern is the angle between them. And what we showed previously was u dot v is magnitude of u, magnitude of v, cosine theta. Now, if we're talking about things that are perpendicular, so let's look at two vectors u and v that are perpendicular. Let's call this vector ub, and let's call this vector u. And let's say the angle between them is pi/2. Okay, so this is a right angle. We'll call that angle theta. What can we say there, right? If the angle theta is pi/2 or 90 degrees, what can we say? What will u dot v be? Well, based on my picture, neither u nor v is the 0 vector. So I get u dot v is the length of u, whatever that is. I don't care that much, frankly, times the length of v, whatever that is, times the cosine of pi/2, cosine of 90 degrees. The cosine of pi/2 is 0, so what we get is we get u dot v is magnitude of u magnitude of v times 0, or u dot v is 0, which was indicated on what we had on the previous page. Remember, we had those two lines that had the two direction vectors u and v, and the direction vectors had a dot product of 0. And we just said here that if they are orthogonal, the dot product is going to be 0, which brings us to a fact. And just let's say that u and v are non-zero vectors. So u is not the 0 vector. V is not the 0 vector. Note, check your textbook to see what they say, but most authors believe the 0 vector is orthogonal to everything. That's typical, but check your textbook for that. Anyway, here's what we're going to know. Here's what we're going to say. If u is orthogonal to v, then u dot v is 0. And similarly, if u dot v is 0, then u is orthogonal to v. So something for us to think about, it's essentially an equivalence, at least for non-zero vectors, that if the dot product is 0, the two vectors are orthogonal. If the two vectors are orthogonal, then the dot product is 0. So what do we want to do with that? We want to think about this thing from a geometric perspective. Now, this works for two-dimensional vectors, three-dimensional vectors, n-dimensional vectors. This is a standard concept. So what are we going to say here? Let's create a vector u, which is 4, -1, 3. And what's my goal? Find a non-zero vector v such that u is orthogonal to v. Find a non-zero vector v such that u is orthogonal to v. So we're dealing with 3 dimensions. So if I have this vector, I could have one orthogonal to it, perpendicular to it in that space. But think geometrically, how many vectors would be perpendicular to a given vector? What will that be? So I have my vector u. I need the dot product to be 0. So can you construct one? Can you construct a vector v such that the dot product with u would be 0? And if you can, do you think it'll be the same as the one that I'm going to construct? So here's my first attempt. 4 times 1 is 4. -1 times 1 is -1. 4 plus -1 is 3. So I need -3, make this -1. Right now I can see what? I can see u dot v equals 4 times 1 plus -1 times 1 plus 3 times -1 equals 4 minus 1 minus 3 equals 0. The dot product is 0, so what is my conclusion? Conclusion, u is orthogonal to v. Find another one. So again, u is 4, -1, 3. What could v be? How about 0, 3, 1? Again, we're going to check to see what u dot v is. U dot v is 4 times 0 plus -1 times 3 plus 3 times 1, 0 minus 3 plus 3 equals 0. So u dot v is 0. So indeed, there's an infinite number. So as you're trying to visualize this, you start with the given vector. Maybe this one right here, standing straight up from my paper. And anything within that page, any vector that would live within that page would be orthogonal to it, if you can see that. Get the idea. So as long as the dot product is 0, we're going to have a situation where the two vectors are orthogonal.